In this video, I want to talk about arc length of a curve described by a vector function. Now, I'll remind you that back in Calc 2, we did arc length when you had a curve described as y equals some function of x. And like most things in Calc 2, the way we did it was to take the interval from a to b, and so I'm looking for the length of that curve. And so I take the interval from a to b and I cut it up into n equal pieces. They don't have to be equal, but generally we do make it equal so that the calculations are just a little easier to do. And then for each little subinterval here, you're looking at a little bit of arc length. And we calculate the length of that arc, we estimate it, that is, by looking at a little triangle there. And if I zoom in on that triangle, there's a little bit of change in x here, and there's a little bit of change in y there. And we call the diagonal length there a little bit of change in s, where s is representing arc length. And there is, of course, a Pythagorean relationship between the three of those variables. And so ds is equal to the square root of dx squared plus dy squared. And in a typical Calc 2 class, what we then say is, oh, look, we can factor out a dx squared from everything in here. So ds is the square root of dx squared times 1 plus dy dx squared. Right? And then the dx comes out, and we got the square root of 1 plus dy dx squared times dx, and of course then the integral of that the arc length would be the integral from a to b of this thing, 1 plus, and the derivative here is dy dx is the derivative, so that's f prime of x squared dx. Now, what I want to do is something very similar, but when we're talking about vector functions, we're really looking at a parametric curve. So I'm going to have, essentially over here somewhere, you've got your parameter, right? And in the parameter, it's going to go from a to b. And that will then correspond to some curve over here in the xy plane, starting at t equals a and ending at t equals b. And we want to figure out the length of the curve all the way around here. Well, the way we do it is not unlike what we did up there. We take the interval from a to b here and chop it up into a bunch of little pieces. Each endpoint here then will correspond to a point somewhere along the curve. And I'm purposefully making these not equal length, even though these might be equal length here, the parameterization may not space them equally in the xy plane. Or if this was 3D, you'd have x, y, and z, of course. But each one of those little segments here, those little bits of curve, we approximate by a straight line segment where, again, there's a dx here and there's a dy. Now, if this was in 3D, there would also be a dt, right? A little change in x, a little change in y, a little change in z, right? And the arc length, ds, is that diagonal. And again, there is this relationship right here. Right? Now, instead of factoring out a dx squared, let's factor out a dt squared. And this always seems funny to me. Having taught for many years, you have students say, what, there's not even any t's in there, how can you factor something out? It's like, well, think about this. 3x plus 7. Can you factor a 4 out of that? It's like, well, yeah, you can, because this would just be 4 times 3/4 x plus 7/4, right? That is, by factoring something out, you're writing the thing you're factoring out as a factor, and then whatever's left is divided by the thing you factored it out, so that if you multiplied it back in, you'd be left with what you started with. So that's what I'm going to do to this thing. I've got this ds equals the square root of dx squared plus dy squared, and I'm going to factor out a dt squared. So ds is the square root of dx squared divided by dt squared plus dy squared. Come on now. dy squared divided by dt squared. All that's times dt squared. And then you can say, well, pull that out of the square root. So I've got ds is the square root of, let's just call this x prime squared plus y prime squared times dt, where x and y are, I probably should have written this to begin with, that I have my vector function r of t is x of t comma y of t. Right? So x is the first component of the vector function, and y is the second component of the vector function. So I can say dx dt is the derivative of that x component, and dy dt is the derivative of that y component. And then the arc length will be the integral, starting to finishing, a to b, of this thing, the square root of x prime squared plus y prime squared dt. Now, there's another way that I want to write this, which, if you're taking the course in the order that it's presented in the winter of 2021, we haven't actually talked about position, velocity, and acceleration and things like that quite yet. But this is the nature of knowledge and the nature of learning. Time is linear. I can't move back and forward in time. I can only present things to you in one order. But yet the knowledge of one thing helps you with the knowledge of something else, and vice versa. And so it's always hard to say which order to present them in first, because they don't even know I don't know what order to put them in, because each relates to the other. So even though we haven't talked about position and velocity, I'm going to quickly say this. If the vector function is thought of as a position function, what's your position as respect to time, then the derivative, this is position, if t is time, then the derivative of the position, that is the rate at which your position is changing, is the velocity. So r prime of t, which I would call v of t, is the velocity vector. And we have already seen that the derivative is a tangent vector. So the velocity is something that's pointing in the direction that the object is moving. And it turns out that the length of the velocity vector, the length of that vector, is what we call the speed. It points in the direction of motion, and the length is the speed. We will expound on this in a later video. So what I'm looking at here is this is precisely the length of the velocity vector, because the position vector up here, I scrolled a little bit too far, the position vector is x of t, y of t, so the velocity vector would be the derivative, which would be, take the derivative of each piece, right? X prime of t, y prime of t. And of course, if this was in R3, we would have a z prime of t here. Okay. And the length of this vector is square the components and add them up and take the square root. That's exactly what we have here. So this is sometimes written as the integral from a to b of the length of r prime of t dt. And sometimes it's written as the integral from a to b of the length of the velocity vector. They just write it as v, right? And this makes a lot of sense to me, because if I want to figure out how far something has gone, an object that moves, a particle that moves from here along the curve to there, and I want to find out the distance that it travels, well, distance equals rate times time. Speed is a rate, how many miles per hour, feet per second, meters per second, whatever it is you're measuring distance with and time with, right? But this is a velocity, and then times a little bit of time. So you have a certain velocity for a little bit of time, and then you have another velocity for a little bit of time, another velocity for a little bit of time. Each velocity times time is a little bit of distance, and then you add them all up, right? All those little bits of distance to get the total distance traveled along the curve. So the arc length is the integral from starting t value to ending t value of the length of the derivative vector dt. let's do one example to show you how this calculation might work. What I want to do is I want to take a look at take an example that I can actually calculate the arc length a different way to double check to see that it's doing what I think it should be doing. So I have here the helix. So with respect to x and y, it's just a circle, a unit circle, but then there's a t here in the z component. So in your x, y, z space, right, this is at t equals 0, this is x, and this is y, and this is z. T equals 0, I'm right here, and as I go around the circle, the z value is going to climb so that after one time around, you've moved up to a height of, well, one time around for these would be 0 to 2 pi. So this is t equals 0 here, and t equals 2 pi at the end there. And so the height is going to be the same as the t value, right? Because z equals t. So there's a 2 pi for the height there. So I want to find the arc length around that one piece of that one cycle of the helix. Okay? So in order to do that, according to the formula we have up here, I need to take the derivative. So r prime of t, this was a vector, so is this. R prime of t is take the derivative, so minus sine t cos t 1. And then I need to know the length of that. So the length of the derivative vector, sometimes called the length of the velocity vector, right, which would be the speed, is the square root of negative sine when I square it gives me sine squared, and cosine when I square it gives me cosine squared, and then plus 1 squared, which is 1. Something nice here happens because the square root, sine squared t plus cos squared t is 1, so I end up with the square root of 1 plus 1, which is the square root of 2. Okay? This is what I would call constant speed. That is, my speed here as a function of t was just a constant. So that if you think about an object that moves along that curve with this parametrization, it moves at a constant speed. So when I drew those subintervals before, I made them different lengths. In this case, they would all be the same length because it didn't depend on t. But anyway, now I need to do the integral from starting point t equals 0 to ending point t equals 2 pi of the square root of 2 dt, and this should give me the arc length. And does that work? I've got, well, the integral of square root of 2 is just square root of 2 times t, evaluated between 0 and 2 pi. And so I get 2 radical 2 times pi minus 0. So that looks to be like what the arc length should be. Now I say I have another way of thinking about this because this happens to be a really nice curve. If you think about the cylinder, x squared plus y squared equals 1. It's a cylinder of radius 1, right? And it parallel to the z-axis. This curve is completely on that cylinder. You could cut the cylinder open right through here and unroll it. And so what would happen to that curve when you unroll it, it turns out, because the z is a linear function of t, that this would just unroll into, right? So if I looked at the cylinder from there up to that top point there, all the way around, right, that it would unroll into this rectangle with the diagonal drawn across it. Right? Well, I know the height of the rectangle. The height of the rectangle is from here up to there, which is 2 pi. I can figure out the length of this rectangle because it's the circumference of the unit circle going all the way around there. Well, the circumference of the unit circle is 2 pi times the radius. Well, the radius is 1, so this is 2 pi. How long is that diagonal? Well, with these two lengths the same, you're looking at a 45-45 right triangle, which typically I draw as 1, 1, the square root of 2, but now scale everything up by a factor of 2 pi. So this is going to be 2 pi times the square root of 2, which is precisely what I have right there. Okay. Now, One of the things I want to point out is that this integral right here, this integrand that you're trying to integrate, is usually not particularly nice. Textbooks have a tendency to pick really crazy looking parameterizations here so that when you come up to this point, it will be something you can do by hand. Okay? But in general, this is not easily integrable. I do not expect you to do these by hand. You can have a calculator, you can have a computer do the integral for you. Even your TI-82 can do a definite integral, right? So don't feel like you are obliged to do every one of these by hand. Use your calculator. Okay. Anyway, there you go. Arc length.